Hi everybody and welcome to this short lecture about how to make your own radio CCTV camera. Today I'd like to show you this small device here, which is the RunCam Nano 2, a drone FPV camera outputting an analog signal here. You can power it at 5 volts and it outputs an analog PAL signal on the yellow line. And here on the left we also have this nice board from Adafruit, and here on the left we also have this very nice board from Adafruit, allowing us to display an analog PAL signal coming from here on the yellow line. So again, we can power this board here at 5 volts on the red and black lines, input a PAL signal on the yellow one, and we are gonna see the PAL video on this display here. So let's check this camera out on this board here. Okay, so let's see how I connected all these things. First, I've got these two wires here, red and black, coming from my bench power supply, which is set to 5 volts right now. And over here I have a crocodile to connect the ground and the power of my PAL visualization board as well as the camera, because if you see here I use the same crocodile to power the camera at 5 volts. So power, ground, and here I use this yellow crocodile to bring the signal from here to here. So here I use this blue line, this blue cable to go in this connector here. And we don't care about the white, which is the audio, we just care about the yellow, which is the video. So I take the signal from here, from the camera, and I put it in the yellow line here to the board. So let's now power this thing on. Perfect, look at this. This is our camera. And as you see, we can visualize the image on our display. So the camera is working and the board is showing us that we have a PAL signal. So let's now see on the oscilloscope how this PAL signal looks like. Okay, so this is our camera, which is powered on with our bench power supply. And here on the oscilloscope you can see the PAL signal being outputted from the camera. We are gonna have a deeper look into how the PAL signal looks like, but for the moment notice the following. If I cover the camera, the signal doesn't have many details. If I leave it, the signal is full of details, and if I cover it again, the signal is very poor. So when the camera sees something, the PAL signal contains color, and if the camera doesn't see anything, or everything is black, there is no color to send and the signal is very poor. So at the very beginning I wanted to show you more in detail how our PAL signal looks like. However, I decided not to do that in this video, so in this lecture we are not gonna delve into the PAL signal, and I think that I will deal with the PAL signal more in detail in a future video. So now assume that we want to transmit our PAL video stream from the camera over the radio. Transmitting our video stream over the radio and receiving it from a remote appliance like a TV would allow us to basically build a remote CCTV system. So what we are gonna see today is the FM transmitter. So we want to modulate the video stream from the camera, which is our input signal, with the frequency modulation, and transmit it over an antenna to a remote appliance that is able to receive it, demodulate it, and show it on a screen. Alright? So these here are the basic components of the FM transmitter. First of all, as said, we have our input signal, which in our case is the PAL signal from the camera, the video signal. Typically, in an FM transmitter, we pre-amplify the input signal and send it to a modulator. This block here, called the modulator, takes the input signal and a carrier frequency, namely a very high frequency oscillating signal, typically something like this, and mixes them together. So at the output of the modulator, we have what we call modulated signal that we can see over here. So for example, if this signal here is the message, our video stream, and this signal here is the carrier, or what is generated by the oscillator, if we mix this message with this carrier, we obtain this modulated signal here. If you have a look at it for a moment, you will notice that when the voltage of the message signal is increasing, the frequency of the modulated signal also increases. And when the voltage of the input signal decreases, the frequency of the modulated signal also decreases. So in FM, our modulated signal is the carrier whose frequency is modified by the voltage of the input signal. Alright? My drawing is not so good, but I think that you can understand it. And note that the amplitude of these two signals, the modulated signal and the carrier, is the same. So the modulation itself doesn't change the amplitude of the carrier, just its frequency, because we are in the frequency modulation, right? Then we take our modulated signal and we amplify it. After the amplification, the signal is ready to be sent over an antenna. So the first block that we would like to build is the oscillator. And in order to build the oscillator, we would like to see what is an LC tank circuit. Imagine to have this circuit with a fully charged capacitor here, a switch, and a coil, an inductance here. As soon as we close the switch, the currents start flowing from the capacitor into the inductor, like this, because the capacitor starts discharging to the inductor. And the more the capacitor discharges to the inductor, the more the inductor gets energized and puts all this energy here that was into the capacitor into its magnetic field. When the inductor is fully energized and the capacitor is completely discharged, the magnetic field into the inductor is not fed anymore by the energy coming from the capacitor, and the magnetic field in the inductor starts collapsing, and as a result, all the energy that is stored into the magnetic field of the inductor returns back to the capacitor in the opposite direction. And as a result, we get that all this energy here charges the capacitor again, but in the opposite polarity, okay? So if we look at this from a time perspective, we see that this circuit starts oscillating, right? Because now the capacitor will discharge into the inductor and the inductor will discharge into the capacitor and so on. So in an ideal circuit where we have no losses, no dissipation of energy, this will oscillate forever, right? But the reality is not so nice, because in the reality the circuit dissipates energy, so the oscillations die out. If you look at this graph here, this is the energy of the circuit, and as you see here, if we would have a look with an oscilloscope to this circuit here, we would see this behavior. The circuit would start oscillating with high energy, and then the energy would be gradually dissipated and the oscillations would die out. So how can we build a circuit that sustains oscillations? A circuit that is able to start oscillating and maintaining these oscillations stable. By the way, if we have such an LC tank circuit, the formula of the resonant frequency at which this circuit oscillates is the following, is 1 over 2 pi multiplied by the square root of LC, and is measured in hertz. Our condition is that to sustain the oscillations, we need some external source to compensate the energy dissipation. And our goal here is to build an oscillator, right? So we want to build the oscillator block that we saw before we need for our modulation. And this here is the simplified schematic of an oscillator. Here we have the input signal. This one is an adder. Here we have an amplifier. We define what is called a closed-loop circuit. And in this case, the gain on the input signal that we get with this closed-loop amplifier is called closed-loop gain, and its value is A times beta. In the case here that we saw before where the oscillations die out, namely in the damped oscillations case, we can say that our A beta is smaller than 1. But if we want sustained oscillations, like in this case here, A beta should be equal to 1. In reality, it should be 1 and change because we have to compensate dissipation. And, very important, the feedback on this line here should be in phase with the input signal. These two conditions for sustained oscillations are called Barkhausen criteria. So if we want the sustained oscillations in a circuit, we must meet the Barkhausen criteria. So let's see a little bit in detail what is this feedback oscillator. First of all, we have to say that beta A must be slightly greater than 1 to compensate the physical dissipation, because in a physical circuit we have a dissipation, so we need a gain that is slightly greater than 1. Here is our feedback oscillator, and notice that if we remove the input signal, this circuit here will still produce oscillations. And this seems black magic, but it's not, because we always have white noise into the circuit, and white noise has all frequencies, including the one that meets the Barkhausen criteria for this particular circuit here. So, for that frequency, that is included in the white noise, obviously, the overall phase shift of the feedback is 0, or 360 degrees. And the loop gain, beta A, is 1 and something. And if we realize this circuit, we get the sustained oscillations. Okay, so the type of oscillator that we are going to see today is the transistor-based oscillator. And in this kind of oscillator, we use a transistor as an amplifier, okay? So we have an input signal Vin, which is sent over the base of this transistor here, which is an NPN transistor. The transistor is connected in common emitter configuration, and if we build this circuit, we have at the output an amplified version of the input signal. And very important, this output signal here is not only an amplification of Vin, but is always phase shifted of 180 degrees. So we input a Vin signal, we get an amplified Vout signal which has the same shape but has a higher amplitude and is shifted of 180 degrees. And now let's start with something really serious, the Colpitts oscillator. So this circuit here is named Colpitts oscillator and is built based on an LC tank circuit. We are gonna use something like this to build our FM modulator. So if we have a look at this circuit, first of all we have to say that C1 and C2 build a simple voltage divider. And if you look over here, we have an RF choke, which is basically an inductor, which gives us a high reactance at the oscillation frequency and a low resistance at the DC. So this RF choke here, in general, helps starting the oscillations in the Colpitts oscillator circuit. Let's now analyze this circuit a little bit in detail. First, when the power supply is applied, C1 and C2 charge up. So they will discharge through the coil L, which gets energized as we saw before, and then L will discharge on the caps C1 and C2, and oscillations will start here in the LC tank circuit. The two resistors R1 and R2 provide a stabilizing DC bias here on the transistor base. And the C3 and C4 capacitors block DC. Okay? Then we know that in order for this circuit to oscillate and sustain the oscillations, it has to meet the Barkhausen criteria, right? And as you remember, one of the two Barkhausen criteria is the phase shift of 360 degrees in the feedback. In this circuit here, the 360 degrees phase shift is provided by two things. 180 degrees of phase shift come from the common emitter amplifier, here, and 180 degrees come from C1 and C2 that are in series and in parallel with L. So these two things together give us 360 degrees of phase shift for our feedback. So if we have the oscillations going in this direction here, then we have the feedback going in this direction here. And the feedback has a phase shift of 360 degrees, namely 0 degrees, with respect to the original oscillation. So they add up and we have sustained oscillations. Then what about the feedback fraction beta? Well, beta is the ratio between C1 and C2 and is a percentage. And remember that since we have C1 and C2 in series, the total capacitance of C1 and C2 is CT equals C1 times C2 divided by C1 plus C2. Okay? Then, under all these conditions, this circuit here will oscillate at the resonant frequency of 1 over 2 pi times the square root of LCT. So with all this theory in mind, we come to our VHF-UHF video transmitter. This circuit here is very common, you can find it on the internet, and is primarily used to modulate a video signal for the TV. So this circuit was basically used as a transmitter for the old television. When the people of the 60s, 70s had to transmit the PAL signal and make it receivable from the televisions, we are talking about the old CRT televisions, they used modulating circuits that were very similar to this one. Although this circuit is very old, it's very solid. It was tested over decades, and if you want to build a simple FM modulator, it's great. So it's still functional, it's still valid, and it's perfect to modulate and transmit our CCTV camera signal. So on the resource that I found on the internet, they power this at 9 volts, but I will power it at 11. And I choose a 1 microhenry coil here, so my inductance is a 1 microhenry inductance. As a transistor I use a BC547, which is a very common NPN transistor. I haven't placed this diode here, which is a protection diode, so I simply didn't place it on my circuit. And also here, instead of this 4.7 microfarad cap, I placed a 100 microfarad one. For the rest, including the potentiometer here, I used the original values proposed by this circuit that we are gonna see in a moment. But first I would like to indicate you where is the LC tank oscillating circuit, which is here. So here we have the oscillations and here we have the feedback, as we saw before. And the input signal comes from here and goes here, through the potentiometer, through this 10 picofarad cap here, and basically modulates the carrier, which is the oscillating signal generated by this LC tank. Okay? So the modulated video signal will be transmitted here over this antenna. And as an antenna, I simply took a 30 centimeters piece of wire. So this is the circuit. And it's very primitive. So here I have a voltage regulator because I want to power this whole circuit as 11 volts, but I would like also to power the camera on these lines here. The black and red will be 5 volts. And this 5 volts here is regulated by this regulator here. Here we have the coil, the inductor L. This is about 1 microhenry. We have the transistor, we have the potentiometer, and all the caps and resistors. And if you see this wire here, this is the antenna, right? If I flip this board, That's really poor. That's really primitive. I just wanted to build something functional, quick and dirty. So we are gonna power this circuit from here at 11 volts here on these two connectors. And we are gonna power our camera with these two crocodiles. And we are gonna take our input video signal with this yellow crocodile here, which is this video input. So I think we are ready. We have seen the theory, we have seen the circuit, so let's check it out. So this is my FM modulating circuit. Here from the yellow cable I take the PAL signal from this little camera, which is powered from the red and black, which is 5 volts from this regulator here. And this is the circuit. So now we are gonna test it with this old, small, beautiful CRT television. Now I'm gonna power this circuit at 11 volts and let's see what happens. Okay, and here am I. So the circuit is taking the PAL signal from the camera, is modulating it in FM, and the antenna is irradiating the signal over the air. And here our CRT television is receiving, demodulating the signal and showing it on the screen. So now we are ready to create a PCB of this circuit here.